Good morning, everyone. So, today we are going to start a new chapter, Trees and Forests. Consider a problem that there is a central office and we need to lay wires which is connecting the central office to all the houses. So, one of the simplest approach is this one, and of course, this is a tree if we see in terms of the graph, which means if we replace each house and the office by a vertex, then there are no cycles. The more important problem here is that if we introduce the length to the wires, then what should be the minimum number of the wire length which is required so that the central office is connected to all the houses. So we will discuss it later. Let's consider one more problem. Consider the expression x plus y whole square plus x minus 4 by 3. We need to represent it graph theoretically. This is again important when we have to give data and when we have to consider the things in terms of the data. So this expression can be represented as follows. If we put it like this, then it is very easy to understand by computer that how the data has been given. Again, this structure is a tree because it has no cycles. So a tree is a connected graph which has no cycles, and if it is not connected, I am not saying it is not connected, but a forest is a graph where every component is a tree. If there is only one component, then of course it is only the tree. If it has more components, then it is a disconnected graph where each component is a tree. So a forest is a tree, but a tree is not a forest. Consider this example. So the first graph, this one has no cycles, therefore it is a tree. The second one has no cycles, but it has two components, so it is a forest. The last one has a cycle, and therefore it is neither a tree nor a forest. Try to draw all trees with 6 vertices. Very important exercise to see how the trees can be drawn in different ways. So if you draw it, then there comes 6 trees, and you can easily observe that they all are non-isomorphic. First one is simply a path graph where there are vertices of degree 1 and degree 2 only. Here there is a vertex with degree 5. Here there are two vertices with degree 3. Here there is a vertex with degree 4, so again different from the other. Here there is a vertex with degree 3, and there also the vertex with degree 3. But this degree 3 vertex is adjacent to only one degree 2 vertex. But this degree 3 vertex is adjacent to two degree 2 vertices, and therefore all of them are non-isomorphic, and of course there is no other possibility. The first one is path graph, and the last one is known as star graph. The next observation is that a tree or a forest is always a simple graph, because if a graph has a loop, then it is a cycle of length 1. If there are multiple edges between two vertices, then it forms a cycle of length 2. But tree and forest should not have cycle, and therefore when we are defining a tree, we are not mentioning a simple connected graph, because the simple is trivial thing in a graph. When we are mentioning it has no cycle, so it is always simple. The next concept is leaf. So a leaf is a vertex with degree 1, and in a tree, if a vertex is not a leaf, then it is called an internal vertex. So we need to prove that every tree has at least two vertices. Every tree with at least two vertices has at least two leaves. Very interesting result, and in this result we are going to use an approach which is used many times, especially when we are proving the result related to trees. So to prove it, let us consider P is a maximal path. Even instead of maximal, we can say that a path of maximum length. So P is a maximum path whose end vertices are u and v. We claim that degree u and degree v is equal to 1. It means they both are leaves. Yes. Why is it so? We will prove just for one of the case. So let's say degree u is equal to 1. This is what we need to prove. Assume that degree u is not equal to 1, which means it is greater than 1. It's a connected graph, so it cannot be 0. So let's assume it is greater than 1. Greater than 1, it means that there are two possibilities. It is adjacent to at least one more vertex which is not a part of the path w, or it is adjacent to a vertex which is part of the path. In the first case, we have assumed that uv is a path of maximum length. So if u is adjacent to w, then p is not a path of maximum length. We reach to a contradiction. Therefore, it is not possible. In the other case, if u is adjacent to w here, then it forms a cycle. Again a contradiction because tree has no cycles. In both the cases, when we are assuming degree u is greater than 1, we are reaching to contradiction, and therefore degree u should be equal to 1. Similarly, degree v should be equal to 1, and therefore tree has at least two leaves. Now there comes the equivalent statements. We will prove each one by one. So the first one is, if T is a tree, then it has n minus 1 edges. Now in today's class we are going to have 4-5 questions which we are going to prove by induction. Yes. So this one also we are going to prove by induction. So we will take induction on n. N means the number of the vertices. So let T is a graph with n vertices. If n is equal to 1, then of course 1 minus 1 is equal to 0 edges. So this is trivial. The next one is, let us assume that the result is true for all the graphs with less than equal to n minus 1 vertices. Yes. So consider T has n vertices, and to prove T has n minus 1 edges. Now since T is a tree, so it has a leaf, which means there is a vertex u whose degree is equal to 1. If I consider T minus u, which means I delete the vertex u, then T minus u is a tree with n minus 1 vertices. So by induction, T minus u has n minus 2 edges, and since it has n minus 2 edges, if I put back u, what will happen? The number of the edges get increased by 1, and therefore T has n minus 1 edges. So this is what we have proved. Please try to understand what has been done. Let's say this is the graph T, there is a vertex u. If I delete u, then I reach to a new tree which has n minus 1 vertices implies n minus 2 edges by induction. And from here when you put back u, then one edge get increased and it has n minus 1 edges. So here the idea is I have to find a vertex whose property I know. I know that if I delete it, then what is its effect on the number of the edges, and then I use the induction. Yes, I haven't considered the induction on M because in case of the edges, all the edges are same, all are bridges. We will discuss it later. So it's very easy to prove when I use the induction on N. The next result is a simple graph G on n vertices with k components has at least n minus k edges. Again we will prove it by induction, and first we need to understand that should I take the induction on n or should I take the induction on m. Let us consider any graph, whichever we want, or let's say this one. In this case, if I delete a vertex, especially the middle one, the number of the components get increased by 3. In some other cases, it may get increased by 2, by 1, by 100 also, by 1000 also. But whenever you delete an edge, then either the number of components remain as it is or they get increased by 1 only. And therefore, if I delete an edge, then it is more easy to follow the number of the components. And this is why we consider the induction on M. So now if M is equal to 0, we have null graph, and therefore a graph on n vertices and 0 component has at least n minus, sorry, the components are, when m is equal to 0, the components are n components, so n minus n edges. So in case of the null graph, the result is trivial and holds. So let us assume that result hold on all the graphs with less than equal to m minus 1 edges. So let G be a graph with n vertices, k components and m edges. Yes. Now if I delete any edge from G, then G minus E has n vertices as it is, m minus 1 edges and k plus delta components, where delta is either 0 or 1. Yes. So now G minus E has m minus 1 edges, therefore I can use the induction. So by induction, G minus E on n vertices and k plus delta components has at least n minus k plus delta edges. So G minus E, or for G minus E, m minus 1 is greater than equal to n minus k plus delta. This is what follows from the induction. Now if I take 1 on that side, so then n minus k minus delta and plus 1. So either the delta is 0 or delta is 1. In both the cases, this quantity is greater than equal to n minus k. Therefore, m is greater than equal to n minus k. And it means that the number of the edges are at least n minus k. That proves our result. So again, try to understand that first we need to choose that we have to use the induction on n or m. Here if we have used on n, then we cannot trace the number of the components, and therefore we prefer to use on m, because when I delete an edge, then the number of the components remains as it is or get increased by 1. The next question is, T has n minus 1 edges and is connected, then it implies every edge is a bridge. This is from 3 to 4. Yes. So to prove this one, we will use the result which we have just proved. Please think by yourself that how this result has been used. So the above result says that a simple graph on n vertices with one component, which means a simple connected graph has at least n minus 1 edges, and it is already given that T has n minus 1 edges. So simple connected graph has at least n minus 1 edges. It means if you delete an edge, the graph becomes disconnected, which means that every edge is a bridge. So T is a simple connected graph and it has at least n minus 1 edges, and therefore if you delete any edge, it becomes disconnected, which implies that every edge is a bridge. Using degree sum formula, show that every tree containing a vertex of degree k contains at least k leaves. Very interesting result. It says that within a tree, if there is a vertex with, let's say, degree 5 or maximum degree is 5, so it guarantees that the tree has at least 5 leaves. We have to use the degree sum formula. So to use the degree sum formula, let us assume that there are h leaves. So degree sum formula says that twice the number of the edges, and on this side we will count the degrees. So h dot 1, because h leaves, their degree is 1. There is one vertex with degree k, so 1 dot k, and now the remaining vertices are n minus h minus 1. So h leaves and one vertex with degree k, so n minus h minus 1, and now they are not leaves, therefore their degree is at least 2. We do not know the exact degree, but we know that their degree is at least 2, and therefore this inequality would come, because here it is total number twice the number of the edges, and here we are considering at least 2, and now it's the simplification. So 2n minus 2 is greater than equal to h plus k plus 2n minus 2h minus 2. So these two things would cancel out, and that gives you h is greater than equal to k. K represents the number of the leaves. H, we have assumed the leaves in the tree, and therefore the number of the leaves are at least k. Again, one more question which we are going to prove by induction. So it says that a simple graph contains at least m minus n plus 1 cycles. Again, think that we are going to use the induction on n or m. So if there are, let's say, this is the graph, then by deletion of a vertex in one graph, the number of the cycles get reduced by 3. If you consider this graph, the number of, and if you delete this vertex, the number of cycles get reduced by 2. So it means that we cannot trace the number of the cycles by deletion of a vertex. But whatever edge you delete which belongs to a cycle, let's say you delete this edge, then you will have a graph like this one. It means here there were 3 cycles and now there are 2 cycles. In this case, you delete any of the edge, you will have, let's say if you delete this edge, you will have a graph. There are 2 cycles, now 1 cycle. So you delete an edge which belongs to a cycle, then the number of the cycles only get reduced by 1. It means you should consider an edge that belongs to a cycle. But how do you know that there exists a cycle in the graph? So the trivial induction step is that if m is less than equal to n minus 1, which means the graph is a tree or a forest, and it implies that the number of the cycles you can assume is m minus n minus 1, which is less than equal to 0, and which means the 0 cycles. So this result is trivial. So assume that m is greater than n minus 1. M is greater than n minus 1, it means there exists a cycle C in graph G. It guarantees, because now it's not a tree, so there exists a cycle. Now assume induction on M, which we have already assumed. It means that if you consider a graph with less than equal to m edge, with less than equal to m minus 1 edges, then the result holds. So consider an edge E that belongs to cycle C. Yes. Now if you consider G minus E, then G minus E has m minus 1 edges. So by induction, it has m minus 1 minus n plus 1 cycles. Yes, and I know that E belongs to a cycle. So when I put back this edge, then the number of the cycles get increased by 1, and therefore G has m minus 1 minus n plus 1 and then plus 1, which is m minus n plus 1 cycles. This is what we have to prove. So again, you can see that we have proved the result by induction on the number of the edges, and we identified a particular edge with a property that it belongs to a cycle. So last question, it says that we know that a tree is always bipartite. Show that a tree always has a leaf in its larger bipartite set. So there are two bipartite set, V1 and V2. Let's say V1 is larger. So V1 must have a leaf. We'll prove it by contradiction, which means that V1 has no leaf. If it has no leaf, it means that degree of all the vertices in V1 is greater than equal to 2. Yes. Now degree is greater than equal to 2. So if these are the vertices, each one degree is greater than equal to 2, which means that the number of the edges in T is at least is greater than equal to 2 times the number of the vertices in V1, because we have just assumed that all the vertices have at least degree 2. Yes. Now V1 is the larger partite set. There are two partite sets, V1 and V2. This means that V1 has at least n by 2 or V by 2 vertices, because it is the larger set. So at least n by 2 vertices. It means number of edges, I am again using this result. So number of edges in T is greater than 2 times, and these are the number of the vertices in V1. I just proved that the number of vertices in V1 is at least V by 2. It means the number of the edges in tree is at least n, but we know that tree has exactly n minus 1 vertices, which is a contradiction, and therefore we can show that a tree always have a leaf in its larger partite set. So that's all from this chapter. Lot of theoretical questions. Please go through it, take your time, and in the next class we will discuss the next part of this chapter. Thank you very much.